Welcome back. So we talked about momentum as one of the integral part of state-of-the-art training algorithms such as ADAM, which we also covered in one of our previous videos. We're going to basically talk a little bit more about momentum from the perspective of bias variance reduction. And our main motivation is that, again, as we saw in our intuitive discussion, momentum leads to some bias that we didn't have in SGD, but the bias vanishes as you're training your model. But the good thing about gaining this bias, which is vanishing, is that the variance drastically reduces. Okay, so then if this is indeed true, first of all, what does that mean in terms of the convergence of our model? Can we actually get faster convergence provably or not, right? And another question is that if we can't get faster convergence, can we design more effective ways to reduce the variance such that we may actually enjoy provably better convergence compared to a stochastic gradient descent? So these are the type of questions we're going to try to answer. All right, so first recall that, again, the gradient estimation perspective and momentum. We said that, again, we assume that we have access to a stochastic first order oracle, meaning that every iteration we can basically sample a mini batch and calculate the stochastic gradient, and that will be a good representation of the total gradient over the entire data set. Okay? So it's unbiased and then has some bounded variance. So this was our momentum, or the way to update the momentum rather. And we talked about that this is actually, from an estimation perspective, a bias estimator of the true gradient. Okay, so you calculate this conditional expectation, use the linearity of expectation, the fact that this is an unbiased estimator, so this can be replaced by the true gradient. However, this is not necessarily the true gradient. Okay, so therefore we have some bias. So what's the impact on convergence, you may ask? So let's assume that our function is LS smooth. Okay, so this was basically, I would say, the first step in analyzing both gradient descent and stochastic gradient descent for LS smooth functions that were not necessarily convex. Okay, so the idea is that, again, we can use the smoothness to study the progress we are making by updating our parameter from one iteration to the next. Recall that our update is basically, in this case, we are not going in the direction of the stochastic gradient, we are going to the direction of the momentum instead. So using this update and using the definition of a smoothness, we basically can arrive at this expression. It's nothing complicated. Now, what we did previously when we analyzed SGD was that said that, hey, my update vector is an unbiased estimator of the true gradient with bounded variance, such that we could actually handle both of these two terms. In this case, however, that's not the case because we have some bias. Okay, so the analysis would be more involved, and it's not clear, at least at first glance, whether it's going to lead to any better result, or even the result we established for SGD. It could lead to actually a bad result, a worse result, if you will. All right. So what we're going to do then, we're going to basically try to precisely characterize the role of the estimation error in the convergence of the algorithm. So we are talking about an estimator which has both bias and variance, and we are using that to update our parameter in every iteration. So what's going to be the final solution? Is it going to be a good solution or a bad solution? Okay. So what's the role of the accumulated bias and variance while running the algorithm for a certain number of iterations? Okay. So we're going to define this estimation error to be just the difference of our estimator and the true gradient. Okay. So if this is 0, it means that we have perfect estimation. If it's non-zero, we may have both bias and variance, or just some bias or some variance, or So in this case, we actually have both bias and variance. Okay? So it's our total estimation error. Okay? Let's recall that if we were to define this estimation error for SGD, we basically had an unbiased estimator. Okay, so the total estimation error in that case would come only from the variance of our estimator, and that would be sigma square. Okay, so in particular, the norm of this total estimation error would be sigma square for SGD. Now we're going to see what is the norm of this estimation error for our SGD with momentum algorithm. Okay, and also what's the role of that in convergence. So first, we're going to basically establish a lemma, which is actually not very difficult to establish. That's why I'm skipping is proof. That says the following, that the norm of the gradient square is bounded by two terms. So term one, which depends on basically the difference of function values at two consecutive iterates, plus the norm of this total estimation error. Okay, so this is actually a result we sort of had for SGD when we talk about this analysis. It's just that we didn't make it as explicit. It was one of the basically steps in our proof. But previously, the second term was basically eta times sigma square. And what we did, if you recall, when we did that analysis, was that we basically summed over time, used the telescoping sum, and then some basic algebraic manipulations, and then we got a convergence result that said that if eta is small enough, the convergence error is low. Okay. But the main idea, therefore, is that this is a term, let's say, that we can handle like we did using in the analysis of SGD. Okay, so telescoping sum and other techniques. This term, however, could be is different. Previously, we had basically eta times sigma square. Eta was small. That meant that we can actually control the amount of variance. Okay, by setting or the error that arises from variance. Okay, so let's look at this as some sort of error. So previously, the error was eta times sigma square. Sigma square was some constant. However, I had this control over the effect of the variance on my convergence, and that was through eta, my learning rate. I would set the learning rate to be small, such that I would mitigate the detrimental impact of variance on my convergence. In this case, however, there is no control. There is no eta here. Okay, so it seems I don't have any control on the role that this total estimation error plays on the convergence of my algorithm. However, if I'm hoping for convergence, it should happen that this guy is small. For instance, if this norm is order of, let's say, eta, again, like the previous case, despite the bias, again, the variance is controlled, but it's not that I'm controlling it. It's just that given the form of the update, it is reduced by itself. Okay? So it is controlled by itself. Hence, the estimation error is small, and then as a result, the convergence error is also small. Okay? So this is basically what we want to therefore see, whether this term is actually something that is small or not. How does the error evolve over time? So let's just say the evolution of the error then. So, and by that I mean I want to see how the error at one time is connected to the error at the previous time. Okay? So therefore, let's consider the error at time t plus 1. As I mentioned, we want to relate it to the error at the previous time. I know that the error at the previous time is basically, again, mt minus the gradient at wt. So I want to make sure that both of these terms appear somewhere. Okay? So m automatically appears given the definition of the momentum and how the momentum is updated. So what I'm going to do, I'm going to add and subtract the gradient at wt. After doing that, I'm going to basically just group the terms, and then I'm going to arrive at this equation, which basically I'm dealing with 3 terms. Okay? So remember what we want. We want the error to be small. Okay, so therefore these three terms should be as follows. Okay, first term is actually quite easy and quite nice. So if for the time we assume that the second and the third term weren't there, the implication of the first term and the fact that the momentum parameter is strictly less than 1 is that the error actually geometrically, exponentially is reducing over time. So if the error, let's say if the momentum is 0.9, the initial error is 1, the next error would be 0.9, the error after that would be 0.81, and so on and so forth. So a very rapid reduction in the error. But unfortunately, we have two other terms. Okay, so if I want the error to be small, those two other terms should also be small. Okay. Now this term also is a term that I would say is nice. Why? Because first of all, it depends on the difference of GT and the true gradient. Okay. So using the property of our oracle, this is a term that is actually 0 on expectation, given that GT is an unbiased estimator. Also, if momentum parameter is very, very large, meaning that it's very, very close to 1, 1 minus beta is very, very close to 0. Okay? So therefore, this will be a term that is very small, and we can control it by ensuring that the momentum parameter is large enough. The last term would be small if we assume that the parameters don't evolve too rapidly. Okay, so this basically depends on the gradients between two consecutive updates. Okay, the difference of gradients at two consecutive updates. Okay. This obviously it could depend on the loss landscape itself, right? So, for instance, if our function is L smooth with a very small smoothness constant, that effectively means that this difference is just L times the difference of WT plus 1 and WT. Okay, so if L is a small, this will be a small. Also, if let's say I'm using a very small learning rate, okay, such that the difference between WT and WT plus 1 is not too large, this term will also be small again. Okay, so therefore, overall, by controlling the momentum parameter such that it is very close to 1, and by ensuring that the learning rate is small, we should be able to establish that the error is small. Therefore, we should hope that we indeed get some convergence guarantees. Okay? So we can actually formalize this discussion to arrive at this lemma. In particular, under the stochastic first order oracle assumption, meaning that in each iteration we gain access to an unbiased estimator of the true variance with bounded variance, unbiased estimator of the true gradient with bounded variance. The total estimation error for the stochastic gradient descent with momentum algorithm is going to satisfy the following recursion. So the norm of the error at time t plus 1 is beta, a constant which is strictly less than 1, that's crucial, times its current version plus two other terms. Okay, one term depends on the variance, the other term depends on the expected gradient. Okay, and all terms are nice again because beta is less than 1, so this term can be controlled. The second term depends on 1 minus beta. 1 minus beta is very small, and also as my algorithm is converging, the gradient norm reduces. And finally, the last term is also nice because it's just 1 minus beta square. So 1 minus beta is a very small number, a square is even smaller. Okay? So here I'm just hiding some constant. Okay? And also, this is true when you set your learning rate to be a small. Okay, how small? Some constant times 1 minus beta. Again, remember beta. You should think of it as a constant which is very close to 1. 1 minus beta is a very small number. Therefore, the learning rate is also small. So, all in all, this means that we have a nice recursion for how error evolves over time, and this hopefully will lead to a nice convergence guarantee for our SGD with the momentum algorithm. In fact, that's true. So we can establish the following theorem. Let's assume that our loss is, the average loss that we are minimizing is L smooth, but not necessarily convex. Let's assume that we have access to a stochastic First-order oracle and the samples are statistically independent. These are exactly the same assumption we made when we analyzed the stochastic gradient descent previously. Then SGD with momentum algorithm, where the learning rate is specified to be some constant times 1 minus beta, 1 minus the momentum parameter. When the momentum parameter satisfies this condition, again, this means that beta is very close to 1, such that 1 minus beta is a very small number. We can show the method converges to an approximate first-order stationary solution. With what rate? The rate which is 1 over square root of t. So, unfortunately, we cannot, in general, improve upon a stochastic gradient descent rate when we are talking about SGD with momentum. There are special cases, if you will, where SGD with momentum could actually provably improve upon a stochastic gradient descent, but not in general. Because as we can see here, this is exactly the same rate that we got with SGD previously. Okay. So that's one remark. Nonetheless, the theorem highlights again that the momentum parameter should be very, very large, meaning that it has to be close to 1. Okay, and this is consistent with what we are doing in practice. Okay. Now, another remark is that we talked about normalization in class before, and the nice property of normalization that leads to stabilizing the training in many cases. So we can actually establish a similar result for an SGD, normalized SGD with momentum. Okay, so basically we can form the momentum, but instead of moving along the direction of the momentum, you basically sort of normalize the momentum first, and then multiply by some learning rate, and then update your parameter. Okay. So this, in some senses, I would say, sort of similar, if you will, to integrating adaptive kind of learning rates that also depend on your update vector. Okay. But a similar theorem also applies to this method. Okay. So what's the sort of at a high level again? What the theorem says is that despite having a biased estimator in each iteration, convergence occurs, and the reason for that is that the estimation error is vanishing. Okay, so we had that recursion that meant that the estimation error is nice and is going away, converging to a small number as the algorithm converges, and this is thanks to variance reduction. There is a small gain in bias, there is a small increase in bias, but there is a huge gain in variance reduction. Okay, and the variance reduces as the algorithm converges. So there is a virtuous cycle. Okay. The more I'm updating my model, the more I'm reducing the variance and the bias. And the more I'm reducing the bias and variance, the faster I converge. So this cycle repeats itself such that we get this very nice convergence guarantee. Okay? But this begs the question that, okay, so despite this variance reduction, we could not beat SGD provably. Okay? But are there other ways or better ways to reduce the variance such that we can gain faster convergence compared to SGD from a theoretical perspective as well as from a practical perspective? And this is something that we're going to talk about in our future lectures. Before that, in the next video, I'm going to talk about the proof sketch of this theorem. Very simple, we're not going to go into detail, but I want to basically talk about a template or a technique, if you will, that could be broadly applicable. I'll see you there.